Hello everyone, this is lecture 7 of course PE 645. In the previous lectures we have covered multiple handcrafted features such as first order features and second order features, and we mentioned that we will use these features which are extracted from the region of interests or the ROIs to be applied to the artificial intelligence model, whether you are using a machine learning or a deep learning model. And we need to get a high performance and explainable model. And we explained the Radiomics workflow with artificial intelligence, starting from acquiring the dataset, extracting the feature, preprocessing, developing the artificial intelligence model, training and testing, and reporting the performance metrics until we reach the explainability using an explainable AI framework. In this lecture, we are going to go through the different steps from 1 to 5, from acquiring the dataset until we reach a high performance model, and how we can build that system that can accept the different handcrafted features and produces a metric such as accuracy and sensitivity. So let's start. As we mentioned, the first step is acquiring the dataset, and here we need a dataset that consists of images and masks. The images refer to a certain modality such as CT, ultrasound, PET, or SPECT, and the mask refers to the highlight of the region of interest, such as the stone in the kidney or a tumor in the breast, and so on. In this lecture, we will go through this dataset, which is called COVID-19 radiography database, and it's public on Kaggle. And in the first project, we mentioned how to use Kaggle and download dataset from it. So you can navigate to this link and simply log in and download the dataset. You will find inside this dataset, after extracting it, that there are different folders named COVID, lung opacity, normal, and viral pneumonia. Normal is the normal case, and the three other categories, viral pneumonia, lung opacity, and COV or COVID-19, refer to a specific condition. And these are samples from the dataset and the corresponding masks. Here is for the normal, and normal here refers to healthy lungs that appear clear on X-rays with no opacities or symptoms like cough or fever. And this is a sample from viral pneumonia, and viral pneumonia is a lung infection caused by a virus leading to inflammation and fluid building in the air sacs. And some of the symptoms include cough, fever, chills, and shortness of breath. And this is a case of lung opacity, and here there is an area on a chest, X-ray denser than surrounding tissue, and this caused by infections, tumors, or fluid. And in these cases, they require further stasis to determine the exact cause. And COVID-19 is a viral infection caused by SARS-CoV-2 with symptoms ranging from mild to severe. So we are going to utilize this dataset and try to extract different features from it, and we will use these features to build an AI model. This AI model will learn from these features to make a differentiation or to learn from the patterns to discriminate between the different categories. So when we apply a new case to that learned model, it will predict whether it's normal, viral pneumonia, lung opacity, or COVID-19. As you noticed, we are referring to the lungs. So this is the image, this is the corresponding mask, and there are two ROIs. One refers to the left lung and another to the right lung. And to read medical images or to determine the left and right in medical images, the right of the image is your left and the opposite. So this will be the right lung and this will be the left lung. So you may wonder how we can extract these ROIs, which we will call them multiple objects, from the image, because we were dealing only with a single ROI in the image. Simply, we will get the image, get the segmentation mask, and instead of applying direct bitwise AND between the image and the segmentation, we will first extract the different blocks or objects from the segmentation mask using contours. So if we simply are able to extract that object using the contour and this another object using also a contour method, then we will have two regions or two objects. So later we can use the first object or white region and apply bitwise AND to get the first region. And the same for the second object, we will take it only and apply bitwise AND between it and the original image to extract the second region. And this approach is helpful when you find multiple objects in the image. So wonder if you have an image or a mask that consists of multiple stones in the kidney. So you need to extract the different features from each stone, because sometimes each stone may refer to a stone category or type. Maybe this a stone accumulated from calcium, this may be another type, this may be a third type. So simply we will follow the same approach in different projects so that we can extract different regions or objects from the mask and use each one individually to extract the corresponding ROI. So our code should get the image, get the segmentation mask, extract the different regions, whether it's only one region, two regions, or more. So refer to code 21, extract multiple objects from ROI. Here we are importing the necessary libraries such as OS, CV2, NumPy, Matplotlib, and also we are importing our custom helper file. First, we define the basis for the input images and masks. Here the image, here the mask. Then we define the target size. You can keep the original size or you can resize the image. We defined a threshold called contour area threshold, and we will mention this after a while. Then we checked both the image and mask exist. If not, there is an error. Then we read these two images in the grayscale. After that, we made another check to check that both of them are not none. None here refers that the CV2 package couldn't load or not able to load the case image or the case segmentation. So we are checking here, it's none, then it means that the CV2 didn't read it or the segmentation wasn't read successfully. If any of them is none or both are none, then raise another error. Then we call the function that we are going to illustrate called extract multiple objects that accepts the image, the segmentation, the target size, and the threshold that we defined earlier with a 0 value. Let's assume that this function is executed, and the aim of this function is to return the regions, and regions here is a list that consists of different ROIs, which is in our case this one and this one in the list. After that, we printed the number of regions, and in our case it should be 2. Then we created a figure with multiple subplots. The first subplot contains the original image, and the second subplot contains the segmentation mask, and then we created a loop to loop over the regions and display them one by one. So if we have 2 regions, then we will get another 2 subplots. After that, we save this figure, displayed it, and close to free the memory from the figure. So let's return to this function, extract multiple objects from ROI. You will find this function created in the helpers file that accepts the image and segmentation and the 3 optional parameters: target size, contour, area threshold, and sort by X. And we will illustrate each of them. First, we resized the image and segmentation with the given target size. Then we binarized the segmentation mask to ensure that the image or the mask contains only 0s and 1s or 0s and 255s. You can also apply this method as we did earlier using the threshold function in the CV2 package by giving the segmentation and the threshold. So it will also return a mask that consists of 0s and 1s or 0s and 255s. Whether you use this or that, you will get a mask with only binary values. Then we made a check that the whole mask is not 0s, so we are summing the mask. If it's equals 0, then raise an error that the mask is a black or empty. After that, we did what we said, getting the contours. And to get the contours using OpenCV or CV2 package, there is a function called find the contours. And here we are detecting the contours in the segmentation mask. So we applied here case seg or the segmentation mask. Then we will get the different contours. Then we sorted the contours according to the X coordinates from left to right. But we here added a check to check if sorting by X coordinate is required. And also we added else. And what we are doing here is that the contours returns in some packages or some versions from OpenCV 2 elements. The contours is the first element. So if you noticed here in the sorted function, we are referring to the first index from this list. So what about if we didn't sort by X? Simply, it will raise an exception because here it will say that we are looping on a wrong object. So simply, if we didn't apply sorting, then we will get the first index without any sorting. We added here a check just in case you are using another version or earlier versions that returns only one object, not a list. So if the list contains 2 elements, use the first index, otherwise use the second index. By all means, the aim of this block is to sort the contours according to the X coordinates. Why we are doing that? Because sometimes you may find a wrong image or a rotated image where the left lung comes before the right lung, or this region comes before this region. How is this? Simply, if I told you that the mask is something like that, this is the right lung and this is the left lung. Maybe there is an issue with the lung here that collapsed it to be like that. So if you apply the code, then this object will come before this object. Another case, let's assume the opposite is like that. So when we apply contour to extract the region of interest, the ordering will be different. Is this an issue? Sometimes yes. Why? Because when you are going to extract features, we will mention that we need to extract the features from a certain object or a certain region along the images, and then extract the other region, and then the third region, and so on. So if we mix between the left and right lungs or the different regions, then the features will be mixed up, and this may hinder the model to determine the patterns, because sometimes the left lung may be larger than the right lung and the opposite. So if you have a feature refers to the area or the volume, then the model will get confused, because sometimes the model finds that the area increases with the left, sometimes the area increases with the right, and this will hinder the model from distinguishing between the categories. So simply apply sorting whenever it's required or essential. Then we created an empty regions list, and this will contain the different ROIs. After that, we created a loop to loop over the contours, and at the end, we made also another sorting to ensure that everything is okay and return the regions. Now, what's inside this list? First, we got the area, and the area can be extracted or calculated using the contour area. Then we skipped if the contour area is below or equal to the threshold. So here, this threshold is the minimum area to ignore the regions. So the contour threshold here is a value to ignore the noise or artifacts found in the image. Assume that you got an image, and when you applied binarization, you found an object here, another object here, and a small artifact on the right. We need to ignore this. So in our example, we are sure that the left and right lungs are above a certain value. Let's assume 10 or 20. So we will set this value by 10 or 20 or 30 or any value to ignore any regions or any other artifacts below this threshold. If it's 0, then it will accept all of them as we defined here in the execution and the definition of the variable. After that, we created a black mask. What is the aim? Simply, we have a black mask. We will fill this black mask with the corresponding region. So the corresponding region will be only white and other regions will be black. We got the contour, the current one, using the index I defined in the loop header here. Then we used the fill poly to fill the contour area in the mask with white color. So we have a black image. For the first region, it will be filled with white and other will be black. And in the second loop, it will create another black mask to fill the second region, and so on if we have other regions. Now we have a mask, so we can apply bitwise and now between the image and the new mask and get the cropped ROI. After getting the cropped ROI, we will append it to the regions and then loop to the second iteration and so on until we return the different regions list. Again, we retrieve the regions here and display it. This is an image or an example for the lung that consists of multiple objects, and we executed it again on a single object and it got a correct result. Now we know how to acquire the dataset from a public source such as Kaggle, download the data and it checks the data if it contains multiple objects or a single object, and we know now how to extract multiple objects from the images and masks. Now let's move to the second step, which is called handcrafted feature extraction. And in the previous lectures, we mentioned how to extract first-order features such as the mean, skewness, and kurtosis, the second-order features such as GLCM, GLRLM, and GLSZM. And earlier we mentioned that there is something called higher-order features that uses complex mathematical transformations or filters, and all of them can be combined together in our data or final data to be provided to the model. So let's recap and summarize these features. The first order features capture statistical properties of individual pixel intensities without any relationships between the neighbors. GLCM features quantify the texture by analyzing how often pairs of pixel intensities occur at specific spatial relationships. And here we define distance and angle. For GLRLM features, they analyze the length of consecutive pixels with the same intensity in a specific direction. And GLSZM features, it evaluates the size of contiguous zones of pixels with the same intensity regardless of direction. And here we refer to connectivity, whether it's 4 or 8 in 2D or 6 and 26 in 3D. We can use the first order features if we need to analyze the overall intensity trends without spatial context, and if we need to analyze the texture analysis such as heterogeneity, we can use GLCM features, and we can use GLRM when we require assessing the uniformity of textures such as fibrosis in tissues, and we can use GLSZM if we need to analyze large scale heterogeneities such as lesion characterization. Or we can make a combination between all of them. Here's a summary table that can help you to summarize when to use each feature type, if it's critical to select one of them, but if it's not critical, you can combine the different features or all of them, and then later use feature selection to select the most promising feature. So if you are focusing on the texture analysis, then you can use GLCM, GLRM, and GLSZM. GLCM for fine scale texture, GLRM for directional texture, and GLSZM for large scale texture. But first order feature doesn't extract any texture analysis. Spatial relationships, again, there is no place for the first order features, but if you need pairwise relationships, you can use GLCM. Directional continuity, then you can use GLRM, and SZM if you refer to the isotropic. For the uniformity, you can use first order features for the global uniformity, and GLCM for local, and GLRM for run-based, and GLSZM for zone-based. For the contrast, you can use direct contrast analysis using GLCM, and indirect analysis and insights using the other two features. For the complexity evaluation and regularity assessment, GLCM offer fine scale, while the other two offer large scale. To understand it more, let's assume we have a practical example for medical imaging about the tumor characterization, and here we need to analyze the texture and intensity-based patterns to differentiate between healthy and diseased tissues, assess the aggression of the tumor, or monitor the treatment response. So, if you have these features, first order, GLCM, GLRLM, and GLSZM, each of them will reflect and give insights on some specific things. So in our example, the first order features captures skewness, kurtosis, entropy, mean, variance, and so on. GLCM will get fine scale texture irregularities based on the spatial relationships between the neighbors, and GLRM will get directional streaky patterns and continuity of pixel runs, and it will be zone based for GLSZM. What about its application in the medical imaging or the tumor characterization. So we can say that the first order features can provide overall trends in pixel intensity distribution, and it can be useful for differentiating between the tumors with high or low signal intensities. Maybe you can say the tumor is darker or whiter or brighter than the normal. And you can mention that a tumor with higher mean intensity might indicate necrosis or fluid-filled regions, while higher variance could suggest heterogeneity. So from the value raised for each region, you can assess if it's tumor or not, and what type of tumor. And using GLCM, it will detect changes in the tumor margins, which may indicate malignancy. And you can mention that high contrast or low homogeneity in GLCM features may indicate aggressive tumors with irregular margins. And for the GLRLM, you can assess the fibrosis or linear structures within the tumor. So you can mention that shorter runs may indicate fine fragment textures, such as necrotic regions, while longer runs suggest smoother fibrosis regions. And for the SCM, it can identify necrotic zones or regions or large homogeneous lesions within the tumor. And you can mention that larger zones may correspond to necrotic cores, while smaller zones suggest heterogeneous active tumor regions. So each type of features, such as GLCM or first order, has a specific meaning. One captures the pixels themselves, another captures the zones, a third captures the RAL lenses, a fourth captures the relationships between the current and neighbors and the frequency of this occurrence. So if it's difficult or tedious to handle or understand or get insights medically by connecting between each feature and its meaning, then you can simply attach all of these features together and then use machine learning and preprocessing or different techniques such as feature selection to get the most promising features. And after that, reflect these most promising features and distinguish between the different categories. Then you may simply get some samples from each category and the corresponding values for the most promising features and say yes, for large zones it's something, and for the small zones it's another thing. So whether you start by determining what features you are going to use or use all of them and filter and then get insights and reflect on the data set, the aim of all of that is to understand how each feature contribute and give insights on each category. So the takeaway note here is to use first order features for initial intensity based screening and complement them with GLCM, GLRM, and GLSCM or any other features for detailed texture and spatial analysis. And this multi-feature approach enhances the accuracy and reliability of medical imaging, ultimately improving the patient outcomes. Now, let's return to our example. We have different features, and we have two objects, the right lung on our left and the left lung on our right. And we need to extract the different features from each of them. And at the end, we need to get a table or a CSV file or a file that contains all of these features alongside the category. So simply, we will add our features for the right lung at the beginning and for the left lung at the end. And the last column will be our category. And also we can add here the name of each file. Maybe you can use this later for investigation or comparing between the different cases. But remember, don't include this column in the data that you are going to provide it to the machine learning model. What about if we have multiple objects? Using the same approach, add the first object features, the second, and so on, and the last column should be the class or the category. Now refer to this code, project 2, extracting the features, number 22. First, we imported the necessary libraries and the helpers file. Then we created a dictionary. Inside this dictionary, we defined the different features or the different values or configurations for each feature type. First order features, second order features, such as GLCM, GLRLM, GLCM, and then we defined common values or common configurations such as target size, is norm, ignore zeros, and the max regions. For the first order features, there are no specific configurations, But if you notice here, there is a flag or a configuration called turn on. We defined turn on configuration here, so you can toggle between the different features. If it's false, then don't extract first order. If it's true, such as here, then GLCM will be extracted. For GLCM, we defined D, theta, and is symmetric. And if you notice here, it's a list or a vector for D and theta. And the aim here is that we can set different distances and different angles and extract the corresponding features for each combination between D and theta. The same for GLRM, theta is 0, and it's also a list. And for SZ, it's connectivity, so you can define here 4 and 8, or any of those. As an overall insight from this dictionary, only GLCM features will be extracted because its flag value is true. Other features are false. So, how can we utilize this dictionary in code to extract the corresponding features and call the corresponding functions? First, we converted GLCM theta values and GLRM theta values to radians using NP radians. Then we define our database. Then we got the name of the turned on features so that we can use this name during naming. So we will extract the features and store it in a CSV file. You will find here GLCM-GLRM if you are turning on both of them. Or in our case here, you will find here GLCM. So by the name, you will know what features are inside this file. Then we extracted the classes. If you remember, we have 4 classes. Or if you are not sure, you can define the classes as a static list. Then we got the history as an empty list. And this will contain the different records that we'll use this variable later to store it as a data frame in a CSV file. After that, we looped through each class, got the class path, then we got the files. If you notice, each folder contains 2 subcategories in this dataset. One is called images and another called masks. Both images and masks have the same name, so we don't need any refinement or adding postfix or prefix in the naming. So once you get the files, you can use the names here in both getting images and masks. But for each, you need to define the subcategory, whether you are using images to get the file path or masks to get the mask path. After getting both of them, we can read the image in the grayscale. And here we are applying loop to loop all over the images inside each class. Then we checked if the segmentation is none, or the image is none, or the segmentation is none, then print an error and ignore it or skip it to the next image. Then we extracted the different regions and we sorted them by X to ensure that the ordering is correct. Then, if the number of regions is 0 or the number of regions is greater than the max regions, then continue, ignore, because sometimes some images may contain wrong ROIs or they are scanned in a wrong way, such as getting along here and something like that. So it will detect 3 regions instead of 2. So to avoid all of that, if there are no regions, means it's black, or the regions is greater than the max, which is defined here by 2, then continue. After that, we extracted the features. And image features here will contain the features for all of the regions. And then we appended that record in the history list, beginning with the file name, spreading and unpacking the image features, and appending the class at the end. This will be appended to the history, and by the end, it will be converted to a data frame and saved as a CSV file. So what's inside this loop? It will loop on each region, and inside it, there are 4 checks. One for first, and other for GLCM, a third for GLRM, a fourth for GLSCM. The aim of each is to extract the features, append these features into this dictionary called Regions Features Dictionary, and by the end, all of these extracted features related to this specific region will be appended to the image features. So this will extract for the first region, append it here. For the second region, append it here, and so on. So we will keep track of everything. First, region features are added at the beginning, followed by second region features, and so on. So what's inside this condition? We are using the created function, first order features 2D, pathing region and configurations, getting the features, updating the region features. The same for GLCM, getting the co-matrix, getting the features, appending the features. But here we added two nested loops. If you remember, we created two vectors for the distance and theta. So here we are extracting for each combination between d and theta. The same for GLRM, looping on theta, getting RL matrix, getting the features, updating. The same for GLCM, but now for connectivity, getting the SZ matrix, getting the features, updating. So simply, we are looping on each class, then looping on each file, then looping on each region, and for the specified configurations in each feature, we will make another loop if it's required, or multiple loops if it's required to get the different features, update the record, and after that, we will use the whole history to be stored in a CSV file so that we can later use that CSV file with the machine learning model. So during processing the code and executing it, you will find something like that. It will start, for example, with COV, then lung opacity, then normal, then viral luminia until the end, and it will print the compilation statement. If you tell it only the first order features, you will find something like that, the file, the different features, and if you navigate it to the right, you will find the class or the category at the end. So if you open the file for the first order features, as mentioned, you will find the first column contains the file names, followed by the different features until you reach the last column, which called class, that contains the different categories, starts with COVID, lung opacity, then normal, and finally viral pneumonia. If you checked the header for different features, you will find that it starts with R1 referring to region 1, followed by region 2, and if you have multiple regions, you will find R1, R2 until you reach Rn. Also, you will find the different features here, and if you have features with a specific theta or distance, you will find their values in the header also. So these are the features for the first region, and these are the features for the second region. And it worth noting that some features contains negative values and some features contain high values, such as here, 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 and so on. And some features contains low values, such as this column. So it worth noting to highlight this because we are going to emphasize the importance of normalization when we go to the preprocessing techniques.